what I'm going to do is look not just at the Konza, but at Kansas as a whole. So basically kind of putting the Konza in context of the geology of the whole state, and also looking at just some really basic principles of soil formation, and then applying that, interestingly enough, not so much to the surface soils, although I'll talk a little bit about that, but to what are called paleosols, which are actually the fossil soils that are present in the bedrock of Kansas. And what's significant is that soils reflect both the climate in which they form, as well as the rocks that they're formed on. So we'll take a look at this. So I'm going to look at some things about soils first. So here is a precipitation map of Kansas. And the thing that immediately jumps out at you is that there's a pretty strong precipitation gradient across the state. So out here in the south east corner of the state, you get up to 40 or more inches per year, and you go out here to the western margin of the state, and you're down to maybe 15 inches per year. So there's a pretty dramatic precipitation gradient, and one of the biggest things climate-wise that impact soil formation and development is precipitation. So both the amount of precipitation and how it comes. In other words, is it uniformly distributed over the year, or does it come, you have a rainy season and a dry season? And the other thing that will dramatically impact the kind of soils you get is what the soils are formed on. And that makes it a whole lot more complicated. And I'm not going to discuss that too much. I'm going to focus mostly on soils as a climate indicator. So precipitation, how that precipitation comes, and temperature is also a really important factor. So this is a map of vegetation. Obviously, vegetation is controlled by climate, and vegetation is also one of the main contributors to soil formation. So as you would expect, because there is this very strong precipitation gradient across the state, there's also a east to west vegetation gradient that follows that. So we have right along the Missouri, basically, especially before European colonization, the Missouri was kind of the boundary of the deciduous forests in North America. So you go east of the Missouri, and it would have all been forested all the way to the East Coast. Pretty much, once you get to Missouri, as you go west, it becomes prairie, grasslands. But the grasslands change, again, because of the change in precipitation. So we have what's called tall grass prairie, which is what's here, both in the Flint Hills area and to the east. And then we have a mixed prairie in the middle of the state, and by the time you get to the western part of the state, we're in short grass prairie, which continues on into eastern Colorado. And again, that's all a response to the precipitation gradient. And then, of course, along the main river systems and the alluvial deposits of Kansas, there's sand and sand sage prairies along those alluvial deposits. So, some things about how soils are formed. This is a really simplistic diagram, but illustrates the. Oh, and by the way, please jump up and down or wave your hands or scream at me or something if you have any questions or want me to elaborate on anything. Otherwise, I'll just keep motoring on. So be sure to raise your hand or shout out. Whoops. So the main thing to think about with soils is, again, their vegetation, temperature, precipitation are the main controls. And soils form by vertical processes, that is, by the vertical movement of materials, both fluids and minerals and sediments are moved up and down vertically within the soil profile. So rather than soil processes, excuse me, involving kind of lateral movement of materials, it's basically vertical motion. And the result of that is what's called horizonation, which means that if you look at a soil profile, it has horizontal layers. Okay? And those horizontal layers are a response to these vertical movements. So, what are those? Well, first off, we have leaching. Okay? So this is downward movement. And how much leaching you have obviously is going to be related to rates of precipitation, amount of precipitation. Now, a couple things happen here. One is, you think of leaching as running hot water through coffee grounds, right? So you run the water through a material and it dissolves out the soluble materials out of that part of the soil profile. So if you have a high precipitation rate, it's going to dissolve out those soluble minerals. So obviously any salts, but things like calcium carbonate or other carbonates are going to be put into solution, and they're going to be moved downward through the profile. And the amount of precipitation you have determines how much leaching there is. It's how intense that leaching is. That process can keep on, and you'll see in climates that have very, very high rates of precipitation, more and more less soluble minerals are put into solution. And the things that are left are things like aluminum, is one of the most resistant minerals or elements. Iron, silica. So you end up with these very insoluble, resistant materials left under very high leaching environments. Obviously, in low leaching environments, you're only going to leach out the most soluble things. The other thing is that the amount of precipitation determines whether the material that's leached out of the upper part of the soil horizon gets removed all the way down into the groundwater and essentially removed from the system. Okay? So water will percolate through the soil, carrying dissolved materials. High enough rainfall rates are going to rinse that material all the way out of the profile, and it gets carried away in the groundwater. It's completely removed from the system. Okay? If you don't have much rain, it will just leach it out of the top part of the soil and then precipitate it lower. It'll only move it down into the profile a certain distance, but it won't remove it completely. That'll lead to the next soil process I'll talk about in a minute. The other thing that can also be, it's not really leaching, but is the downward movement of fine-grained materials. So imagine that you have a sediment that has a range of grain sizes in it. Everything from sand to clay, to really fine sediments. And then you keep running water over the top of it. What's going to happen is the fine-grained clays and fine-grained material are going to get rinsed further down into that profile, leaving the coarser stuff at the top. So they'll wash it down between the grains and move it down into the profile. Okay? So the top of the profile is commonly called an eluviation horizon, which means stuff is being removed from it. Then below that, you have a zone of accumulation. Okay, and that can either be things like clays and things that are rinsed down through the profile, or soluble materials in an environment that has a lower precipitation rate that precipitate out, again, further down into the profile. So it's an accumulation horizon. So you have an alluviation at the top, and then accumulation below that. The other thing that adds to the accumulation horizon is that you can get the upward movement of solutions from lower in the profile or in the groundwater. So if you have an environment where you have a high rate of evaporation, okay, so you're drying out the surface, that's going to act like a capillary action, and it's going to pull up water from lower in the profile up. So it pulls groundwater up towards the surface that then gets evaporated. As it gets evaporated, soluble materials will precipitate out. So you can get accumulation of soluble, salts and carbonates and things in this part of the horizon, both from stuff coming down from the top and also from water coming up from underneath. And then at the bottom, you have what's just called weathered bedrock. In other words, where and this could be, doesn't have to be rock, it can also be just sediment, but whatever the original primary material is, gets the weathering processes are beginning. And you get below that, and then you just have unaltered material, primary material. Okay, so everyone has an idea of what's going on here? Okay, so given that things like vegetation and precipitation and temperature, evapotranspiration, evaporation is evaporation of water from the surface, transpiration, anyone know what transpiration means?
It's the evaporation of water from roots.
Okay, right, so that's evaporation that is aided by vegetation. So the vegetation takes up water from the roots. Essentially, the way plants work, vascular plants, is that they're like little capillary tubes. So they suck in water from their roots and evaporate them out their leaves. It's like sucking on the end of a straw. As water evaporates from the leaves, it sucks water up through the capillary system in the plant. And so the plants are pulling water out of the ground and evaporating it back up into the atmosphere. So climate's going to affect all those things. So here's a really simple-minded example of kind of end members, and I'll show you some real soils. So over here, this would be a kind of a soil that you'd have in a temperate deciduous forest, say. They typically label these soil profiles, horizons, given different names. The O horizon is where organic matter is accumulating. Okay, so that's leaf litter and other organic matter that's settling on the surface and decomposing. And then here is the E horizon. That's the eluviation horizon. That's where stuff is being leached out. So the material is being removed from that. And the B horizon is the accumulation horizon. Okay? So that's where the stuff from E goes, or it gets drawn up from down below. And then C horizon is the zone of weathered parent rock or parent material. So in a kind of a temperate forest situation, you have a fairly thick humus layer and a reasonably sized leaching horizons. And mostly what would be in here would be things like clays. Or what's going to accumulate in here. Your really soluble materials like carbonates or salts are going to tend to be completely leached out of these horizons. If you go to the extreme of, say, a tropical environment or an ever-wet environment, you have virtually all leach. No, there's no B here. There's no accumulation horizon. There's so much precipitation that the soil is being completely leached all the way down to the parent rock. So all soluble material is being completely removed from the profile. These tend to be really, really thick, sometimes tens of feet, thick soils, and there's hardly anything in them. Notice they're aluminum, which is one of the minerals that or elements that doesn't move very easily, and iron. So they're basically iron aluminum oxides. This is actually, in extreme situations, the aluminum gets so concentrated in the soil, it forms something called a bauxite. Anyone hear of bauxites? What's a bauxite? It's an aluminum ore. That's where we actually get aluminum from. This is the natural way of concentrating aluminum. So all the aluminum that you use, that we use, comes from soils. Because soils are a natural way of concentrating aluminum. So again, there's no B horizon, no accumulation horizon. Yeah.
Keith, so most of the bauxite deposits where they mine aluminum, originally on top it would have been tropical.
Yeah, yeah. You'd have to have you have to have a really wet, ever wet environment to do that. Then the other extreme is a very arid environment, where you basically don't have any leached horizon, okay, the opposite, okay? And what happens is you have a little bit of rain, right? And that rain will basically rinse the soluble materials, the salts and carbonates, out of the upper very thin part of the soil, but just down a little ways and then it reprecipitates out. And also, because a lot of evaporation, you're sucking up groundwater from underneath, and that precipitates out, and you get a calcite horizon or a calcic horizon. And this is often called caliche or caliche nodules, which you might have heard of. If you go even in parts of westernmost Kansas, certainly when you get into like New Mexico, Arizona, and parts of Colorado, the soils are not quite to this extreme, but they're going to be caliche horizons because the carbonate is precipitating out in nodules. Sometimes those nodules can cement together into a solid horizon, almost like a limestone, but it's actually formed in the soil. Those are called hard pan, which is maybe another term that you might have heard of. So in this case, all you have is accumulation, basically. You're just precipitating stuff out into the soil and hardening it. Okay, so here are actual examples of things, and some of these we'll see, several of these actually we'll see in fossil soils, and some of these are present in modern Kansas soils. So here, this is called a laterite. A laterite is those highly leached soils that form bauxites. And notice that there's kind of nothing going on here. There's no horizonation. They're very thick. Again, they can be tens of feet thick. And the reason they're red is because of the iron. And basically these are iron and aluminum oxides that are accumulated. One interesting thing about laterites and about these highly leached soils, again, these are forming in tropical environments where you have really lush vegetation. And oftentimes people have the misnomer that if you're in the tropics, well, the soils must be really, really rich because look at all that vegetation, right? Some of the densest, richest vegetation you have in the world. Soils are the worst soils in the world, right? There's nothing in here for plants to use, okay? So when in tropical settings, all the nutrients are in the leaf litter. And what happens is a tree falls down, and all the, the fungi and plants and everything go and suck it up and turn it into new plants right away. The soils are very, very poor. And this is significant because of the impact of clear cutting and lumbering in tropical environments. If you cut down a tropical rainforest, you cannot get another one. If you cut down the forest, you've essentially removed the soil. There's nothing there anymore. And best it can support is a poor grassland, which isn't even a very good grassland. But you cannot regenerate a tropical forest because once you remove, there's nothing there. You can't go and plant tropical trees. They won't grow. There's no soil left. There's nothing there for them to grow.
In Vietnam, laterite is all over and heavily used for roads.
Yes.
Used for roads because of this compacting like asphalt.
Yes. Yeah.
That's because of the tropical nature of that part of the country.
Yeah. Exactly. Yeah. Exactly. And in those areas in tropical climates, they often quarry this as building stone because it's very highly densely cemented and hard, and it's used for roads and buildings and things like that. Then this is the opposite example. Okay, it's called a histosol, and this is where you get coals. Okay, so now you have an ever wet or nearly ever wet environment where you have lots of accumulating organic matter. So that's what would become a coal. That's the accumulating peat. Okay, but below it, that's actually a soil. It's kind of gray, this gray clay under here is a soil. It's just a continually saturated soil. So there's virtually no leaching because the water isn't draining out. Okay, you don't get leaching, even though you have high precipitation. You're not leaching it because the water is just sitting there. It's not draining out. And so this is going to be saturated. That's the other thing I forgot to mention with soils. That in order for water to move through the soil, you have to, that's a consequence of the water table. So if the water table's low, then the water is going to drain through that soil down to where the water table is. But effectively here, the water table's at the surface. Okay? So that there's no place for the water to go. It's already essentially down to the water table already. Mollisol, that would be typical of here, of Kansas. A lot of the soils in Kansas would be mollisols. They're typically formed under grasslands. So you typically have a fairly thick organic layer. And this one is actually carbonate. So these are little caliche nodules. So this is on kind of the dry end. So this might be like a short grass prairie kind of environment. So you're having accumulation of organic matter from the grasses, but the rains aren't frequent or intense enough to rinse the soluble minerals out of the soil profile, so they accumulate this would be the B horizons. These are tiny little carbonate nodules. This is would be a wetter environment, again, kind of a temperate, wet climate, where you see here's the organic layer. This is a leached horizon. Often they're bleached out like that. So that's the alluvial horizon that's been bleached out, and then this is the clay-rich horizon. So the clays have been rinsed out of here, down further in the profile, and most of the really soluble materials go be rinsed out of that profile. We'll see some examples of this in the geologic record, or the rock record. These are called vertisols. These form in seasonal, kind of monsoonal, wet, dry climates. So you have a lot of rain in just like a month or so during the year, and the rest of the year it's dry. These are clay-rich soils, and during the dry season they crack and open up. And they also form these structures, which are called bilgi. So these kind of curved surfaces within the soil. And the way this happens is these are very clay-rich, and the clays, when it rains, those clays expand, called expandable clays. So they get wet and the clays expand. Then when it dries, the clays collapse. So what's happening is the soils kind of breathe seasonally. So they expand and they contract. Well, they're not just expanding up and down, they're expanding sideways too. They're expanding in 3 dimensions, right? So if you imagine a soil that's expanding, it doesn't have anywhere to go, right? It's pushing. So what happens is it gets these curved fractures in it, and the soil expands and contracts by doing this. So when it expands and then contracts, expands and contracts, and it does it along the same surfaces. And so every season it's doing this. One place you get these kind of soils is like in the Gulf Coast, which has kind of a monsoonal climate. And interestingly enough, I don't know if anybody here has lived in Gulf Coast, Gulf Coast, Texas, or in that area. But my understanding is that that's what soils are common there. That this is a huge problem for buildings, for roads, for airport runways, a number of things, because the soil is heaving all the time. And it causes collapse of foundations. If you don't treat it right, the heaving, the expansion, contraction soils will crush your foundations. It'll warp the roads, it'll do all kinds of things. So what people will do is install like waterers around their house to keep the soils wet all year round so they don't expand and contract. But it's a real engineering problem in these areas because of the really dynamic movement of the soils. Lastly, caliche soils or calcic soils. 2 examples. Again, this one with these small caliche nodules in the V horizon, and in this one in which those nodules merged to form a solid called hard pan below the surface. So again, very thin soils, essentially virtually no leaching here at all except for this very surface. So the soluble materials are rinsed just a few inches into the soil and then precipitate out, and then also draw up water from below and precipitate out. So you get these hard, dense horizons. And lastly, this is kind of cool. This is what's called a natric soil or salt-influenced soils. This is a soil that in a very evaporating environment in which the groundwater is salty, is saline. And no one really understands why it does this, but it forms this typical soil structure, which is called columnar. So these are like little vertical columns with rounded tops. And it's a soil structure that is typical of soils formed under saline, salty conditions. So my point is here, a lot of the features I've just mentioned are things that actually get preserved in the geologic record, which is kind of cool, which is what I'm interested in. Because if you see these structures, you can relate them to the climate. So now you can go back and you can start saying things about what the ancient climate was 280, 300 million years ago, which again is kind of cool.
Out here in the foothills, when you have a soil bedding like that, how does that all fit in with all of this?
Okay, yeah, good question. Yeah, I didn't talk about the effect of what the soils are forming under. And slopes, that's another thing. Here in the Konza, what you have is these alternations between these hard limestone layers, marine limestone layers, and mud rocks in between. And as we'll see, those mud rocks are actually paleosols. But as far as the modern soils are concerned, so you have at the tops of, so the Konza's terrace, the topography is terrace. It's fairly flat and then slopes and fairly flat slopes. There's flat surfaces, there's terraces are the limestone layers. The slopes are the mudstones, because they're less resistant. So the soils that are on the flat surfaces are sitting on top of the limestones. And around here, a lot of those limestones are really cherty as well. And chert doesn't weather, it just accumulates. So at the tops of those terraces, you tend to have very thin soils. Fairly dry climate here, so the limestone doesn't break down very quickly. If this was in the east, it would be very different. You'd have thick soils developed on top of those carbonates, but not in here, it's too dry. So the result is you have very thin soil. But if you go down either in the valley bottoms, which are alluvial, or on the slopes, which are built on top of more 280 million year old soils, but they're still mud rocks, you get much deeper soils. And the vegetation changes. So you have, your really tall grass is going to be in your valley bottoms or on the slopes. You're going to have a different range of vegetation on the tops of the platforms because the soils are much thinner. That's being controlled by what the soils are forming on. Obviously, the climate's the same everywhere. So, yeah, it's a good question. All right. So now I'm going to move to the geology, but we won't give up on soils because as we go through, we'll look at these paleosols, these ancient soils, and go back to things I've already said about soil formation. So the first thing we'll look at is what are called physiographic provinces or physiographic regions. So first off, I'm sure you're aware of this. This is an elevation map. Okay? So just as Kansas precipitation and climate and vegetation changes east to west, so does topography. So there's quite a difference in topography down here. We're 700 feet or so above sea level. Out here at the westernmost edge of Kansas, we're over 4,000 feet. So we have 300 or 3,500 foot elevation change across the state. So the whole state is sloped upward. In addition, the rocks that underlie Kansas are not exactly flat. They're pretty flat, but they're actually dipping slightly to the west. Okay, so you have the ground is going up this way, exaggerating, but the topography is going up, but the rocks are dipping this way. So the result is the combination of both increase in elevation as you go west, and the fact that the rocks are actually slightly dipping west means that as you go from east to west, you're going up section, you're going younger rocks. So the oldest rocks in Kansas are right here, the youngest rocks are right here. Okay, so as you go from east to west, you're going younger rocks. Okay, so here is a geologic map. I don't know how many people have seen a geologic map of Kansas. A few, okay. So again, notice that again the stripes are kind of north-south, right? And again, that's because both because these layers are dipping slightly to the west and because you're going up slope. And so we start here. I won't talk about the rocks way down here. These are Mississippian in age. It's called Mississippian or early Carboniferous. These rocks here are Pennsylvanian in age, or late Carboniferous. This is the Flint Hills. The Flint Hills are Permian in age. There's a little bit of Triassic here, and maybe a little bit of Jurassic stated, but not much. Over most places in Kansas, you jump right from Permian to Cretaceous. So you jump from, say, about 250 million years or something like that to 140 million years. So there's a big gap. There's what's called an unconformity. A big gap here in which the Cretaceous is sitting right on top of the Permian, except for a couple little bits down here. And then the green is all Cretaceous. Okay, so the Cretaceous actually goes all the way out here to western Kansas, but it's overlain in places by Cenozoic stuff. It's called the Ogallala Formation. So what I'm going to do is the combination of both the topography and the geology, the rock types, produce what are called physiographic provinces that have similarities within that kind of area. So I'm going to go through Kansas looking at each physiographic province. So we'll start over here and we'll work our way west. Wonder. Forgetting that I have power in my hands here. So here is the physiographic provinces. And again, I'm not going to talk about this area here because it doesn't comprise that much of the state. So the Pennsylvanian rocks are form this area, which are called the Osage cuestas. And we'll show you in a second what that means. So this is the Pennsylvanian age stuff. This is the Flint Hills. Okay, so we're right here. So this is the Flint Hills, that's Permian in age. Smoky Hills, this red hills down here, that's Upper Permian. So this is Lower Permian, this is Upper Permian. Smoky Hills is the Cretaceous. And the High Plains is the Ogallala. Okay? So we're going to start here, and then there's the glaciated terrains which will end with up here, which are Pleistocene. So we'll work our way across the state.
Will we get a PowerPoint?
It's being recorded,
Okay.
so you get it that way.
All right.
If there is a demand, I can see about getting slides if there's an interest. But again, this is being recorded. Okay, so we're going to start east and work our way west. Again, jump in, and we can take a break here at some point too if you want. All right, so Osage Prairie, that's the Pennsylvania stuff. Now, in the interest of time, I'm not going to talk about paleontology, which is near and dear to my heart, but I won't be able to talk about it. Simply because I just don't have enough time. So I'm going to be focusing just on the geology, on the rocks, not on the fossils. This is Osage cuestas area. These are, again, Pennsylvanian in age. It's a little hard to see here, but a cuesta is an area where the rocks are gently dipping. Remember, the rocks are dipping slightly to the west, right? And there are limestones within the Pennsylvania, just like they are in the Permian, early Permian. And those limestones are more resistant in this climate to weathering than the shales and sandstones and mud rocks that are in between. And so the limestones make a bit of a ridge or a raised kind of cliff, and then extend back. So this would be sloping back to the west, and then there'd be another ridge, and then it would slope back. So you get kind of a cliff, and then it slopes back, and then a cliff, and then it slopes back. Okay, so that's a cuesta. That's what the word crest is.
Gradually rising in elevation
Yeah, gradually rising elevation toward the east.
towards the east.
Toward the east, because all rocks are all sloping. So you have a limestone here that's dipping that way. So it's eroded off the top, so that's sloping down. But then there's the next limestone here. So there's a cliff, and then it slopes down. There's a cliff, and it slopes down. So that's west, and this is east.
But
So-
you're still going up in elevation as you go to.
Yeah, it's stepping up. It's like going up a series of steps, but the steps, each tier of steps is actually sloped in. So yeah, that's a way to think about it. It's like going up a staircase, but each step on the stairs is sloped.
But you're really going down.
You're actually going up.
That's my question.
The surface goes up.
Yeah, everything's rising.
Yeah, you got, each one is rising.
Yes.
That's my question.
Right. Yeah. Each time you're, but very very gradually.
Yeah, to the west, yes.
Yeah. There's another question in the back.
Yeah, is there a reason that limestone slopes? I mean, it was deposited there by oceans, do you think it would be level?
Well, there is some, again, the geology of Kansas and the mid-continent is fairly undisturbed structurally, but not completely. So that's why the beds are dipping slightly. So there are broad upwarps and downwarps on a large scale. So that's what's creating these slight dips, so that the rock layers aren't absolutely horizontal. So there's these warps, very, very gentle basins and domes, or basins and ridges, but again, very, very subtle. So here is what the world looked like at this time. So this is about 300 million years ago. So all the continents were together in a supercontinent. It's called Pangaea. And a couple things to note here. One is this is the Appalachian Mountains. So that at this time, this was the end of what's called the assembly of Pangaea, with a single supercontinent. And so what's now Africa and Europe had collided against what's now North America and pushed up this giant range of mountains, much like the Himalayas, except much longer. It's actually a much more extensive mountain range than the Himalayas are. It formed in the same way. That stretched all the way across the center of the supercontinent. And this would be the Urals up here. Right now, those towering Himalayan scale mountains are, they call them mountains out there, but they're really just tall hills, right? So notice where we would be, a couple things. Notice there's an inland sea here, that is an ocean that's covering the continent. And we'll see that was episodic things. And Kansas would be right about there, about 10 degrees north latitude. So at this time, Kansas would have been about 10 degrees north of the equator. What's going on down here? This is an ice age, okay? Much like the Pleistocene, except it was the southern hemisphere that was glaciated, not the northern hemisphere. So that's very significant, okay? So that, and this ice age continued. Remember, ice ages are episodic; they come and go. But this period of essentially ice, what's called an ice house climate, existed from the Pennsylvanian through the early Permian. And it was continental glaciation in the southern hemisphere. So, what do the rocks look like that were produced during this time? Here's an example. We have these limestones, these thick limestones, which were formed in the shallow sea. We have shales, as well as sandstones that were formed by Sandstones were formed in by meandering river systems. There are also, within some of these shales, there were coal beds that had underneath them these particularly saturated soils that are preserved under the coal beds. So those were terrestrial environments as well as the rivers. So what we have here is alternations between terrestrial conditions and marine conditions. So here's another example. Again, thick limestones, there's sometimes some thin black shales in there. There's actually deeper water environments, but marine, so marine black shales. But this is a coal bed here, and then a soil underneath it. So there's a coal bed, and then a limestone over top of it. So this would have been a ever wet climate, right? So a wet, moist, ever wet climate here, terrestrial environment, and then shallow marine, shallow sea. What's going on there? Here's a close-up of a coal bed. So get a limestone sitting right on top of it, and here's a coal bed. And then underneath that would be these soils. And again, what I don't show here is the river deposits that are also very common in Pennsylvania. So what we have is these alternations between terrestrial environments of various kinds and shallow marine. And that'll continue all the way through the early Permian. Why is that happening? Well, remember, this is a glacial time, right? So during ice house climate, during a glacial time, the ice just doesn't advance and then retreat, and that's your ice age. Okay? Actually, what's happening is the ice advances a bit and then retreats, and then advances. So if you're going through a glacial period, it's pulsational, like this, as the ice advances, and then it melts back, and it melts back the same way. Okay? So it's pulsational. Every time the ice advances, where's that water coming from?
Out of the sea.
Out of the sea, right? Water evaporates from the ocean, goes into water vapor, precipitates out as snow, right? Rather than rain. That snow gets compacted into ice. What's happened is now the hydrologic cycle is interrupted. That water doesn't go back into the ocean again. It's being stored as ice. So you're evaporating water from the ocean, turning it into ice. Evaporating water from the ocean, turning it into ice. So what happens to sea level? It goes down. So global sea levels fall, right? Now, the ice retreats. Where does that water go? Back into the ocean. What happens to sea levels? Go up, right? So from the Pennsylvanian through the early Permian, the global sea levels are going up and down like a yo-yo on a fairly frequent cycle. Okay? So all the shallow or low elevation areas of continents are periodically flooded. So that's your limestones, your shallow marine limestones. Sea levels fall, terrestrial environment. Gets vegetated, gets soils, rivers, things like that. Sea level rises, limestone. Sea level falls, terrestrial. Sea level rises. So that's why you have these repeated alternations between marine and terrestrial environments.
When we're talking about like shallow seas and deep seas, what kind of depths?
That's a very excellent question. One that is still debated to some extent. I think maybe there's beginning to be a little bit of a consensus, but there's still a lot of arguments. I would argue that you're probably not dealing with water depths more than a few tens of meters, maybe 100 feet, maybe a little more than that, maybe a couple hundred feet at most. That's kind of my sense. Pretty shallow. Yeah, you're not talking about oceanic depths, because we're on the continent, right? Okay, it's called epicontinental sea. This isn't oceanic. This is a flooded continent. But the cool thing is they preserve the same kinds of features, physical features that you see in a modern soil, so you can infer climate from them. So these are what are called vertic soils, and what you're seeing, see these waves, these humps. Okay, those are those gilgi that I talked about. Okay, so this is called a vertic soil, and this was formed in a monsoonal climate, a wet, dry climate, and this is the surface of one of those hummocks. And notice it's all striated, all smooth and striated. Oh, this is, by the way, it's more unfortunately. This is in Spillway after the flood in '93. It was absolutely spectacular.
Where did you say?
Spillway,
Spillway.
Tuttle Creek Spillway.
Oh, still on.
It's also a filter.
Yeah, different rocks though. Yeah. And it's either now, this is actually all under concrete now. And the lower part is all grown up. You can still see some stuff, but it's nothing like this. It's absolutely spectacular. But anyway, what you're seeing here is these striations. And remember I said in these soils, these expansion soils, the soil's doing this, right? Expanding, contracting, expanding, contracting. So the clays in it get smeared out. You think of the soil moving like that, smearing, 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 smearing. And that's what you're seeing. That's what you're seeing here is those clays being smeared out from this moving soil. Notice also that it's this olive green color. That means it's the colors are usually has to do with the oxidation state of iron. So if it's green or gray, it means it's reducing. If it's red, it means it's oxidized, it's hematite or rust, right? Take iron out and rust. So these soils all have iron in them, right? So if the soil stayed wet or wet for part of the year, they don't get oxidized. Because to oxidize, you have air in the soils, right? So if they stay wet at least part of the year, they tend not to oxidize. So they have a gray or green color. If it's a drier climate and the water table is lower, there's air in the soil, it oxidizes, and they turn red. So that's what these are. So these are called calcic soils. Now this is this upper part is actually vertisol, but this is the calcic soil. This is another one. This is also from the spillway. And these are caliche nodules. We already talked about those calcite nodules forming in soils. This is the same thing, except this is kind of cool. These are called rhizocretions, and they're carbonate-coated roots. So the plants are rooted down into the soil, and remember they're sucking up water. So they're drawing the water to themselves, or pulling the groundwater to the roots, and therefore they're drawing these waters that are supersaturated in carbonate to the roots, and so the carbonate precipitates out along the roots. And so they're called rhizocretions, which means accretions around roots. So this is kind of cool. So these are actually, you can imagine, there's one, you can see the roots splaying out as they go down deeper. It's pretty spectacular, yeah.
Would you call that is that fossilized plant material?
No, there's
Or
no plant material in
This
there.
is the shadow of it.
Exactly. Yes, you think of it that way. Yeah, it's. There are also other kinds of root traces in here as well, clay-filled root traces, but very little. There's some, but very little preserved organic matter because it all gets eaten up. It doesn't get. Soils are a really lousy place to preserve stuff. There's just all this stuff living in it. That any organic matter that's there gets scarfed up and.
And where's that picture taken?
This was, I can't see it anymore. It's in the spillway.
It's in the spillway too, that's 110.
Yeah.
This is theirs.
This, I forget where I took this, to be honest.
That looks like it's on the
Big-
bikini, isn't
big-
it? Where you see something similar.
Yeah, there's lots of places that look very similar to that. I honestly don't remember where I took that. It's near here. It's in Riley County. It is. Actually, you can see this, not this exact place, but up on the side of the spillway, not on the floor, but on the side. This unit is exposed. You can still see those rise accretions there. So, yeah.
Where does, or how does the flint accumulate in Nautilus?
Okay, good question. The flint is associated with the limestones rather than with the paleosols or the mudstones. And it's actually it's a chemical reaction, and a couple different things happen. One is that in some cases the silica, which is what forms flint, evaporates, particularly gypsum nodules. So the gypsum dissolves out and the molds that are left behind get filled in with silica and become these kind of cauliflower-shaped chert nodules or silica nodules. If you cut them in half, they actually have like a starburst pattern inside them. But also, they can replace, anytime there's a kind of contrast in porosity or the characteristics of the carbonate original limestone, will preferentially replace those areas. So they can replace burrow structures. Actually, a lot of the chert nodules are actually replace burrows. Sometimes if you see an area that's fairly well exposed, you'll see these kind of branching or networks of flint nodules. Those are called burrows that have been certified. And also, individual fossils can be replaced by silica. And the reason is silica and carbonate, or silicon dioxide and calcium carbonate, dissolve and precipitate under opposite environments. So if you have a more low pH environment, that's going to dissolve your carbonate, but silica precipitates under low pH conditions, and vice versa. So the conditions under which carbonate precipitates are the conditions under which silica dissolves. So they replace for each other. So you get carbonate replacing silica and silica replacing carbonate. So actually the chert essentially grows in the limestones. It grows chemically within the limestones. And you can actually see at boundaries of the flint nodules. You might see a fossil that's half in and half out. Or if you look in it inside of a chert nodule, you can still see the remnants of fossils sometimes. So the chert nodules actually were once limestone, but they've been replaced chemically by silica. The big question with silica, with the flint nodules, is where the silica came from. I'm always asked that, and the answer is the same. We don't know. Nobody knows. Because it requires a lot of silica. The problem is that there's nothing, the rocks above us have been stripped off. One common source of silica are ash beds. Volcanic ash beds have a lot of silica. And there are volcanic ash beds in like the Cretaceous rocks. So if there were Cretaceous rocks above us at one time that have been removed and that had ash beds in it, well, that's possible. They can be produced, silica can come from sponges, from siliceous sponges. Well, there's some siliceous sponges, but not really enough siliceous sponges to produce the silica. There's been a variety of explanations. Also plants. The current grasses that are in the prairie's been here since the Miocene, so it's been around for tens of millions of years. what makes grasses rough, and you know, we like sometimes cut yourself on a grass blade, okay, is little bodies, little silica bodies that are microscopic bodies that are embedded into the plants. And actually, when they burn on the prairie now, they monitor the groundwater, and every time they burn, the silica content in the water spikes up because you're burning all that grass. All the silica bodies are now dissolving because they're just little tiny amorphous silica bodies, and they dissolve into the water, and you increase the silica content. So actually, I passed retired geology faculty here at K-State, Paige Twist, which some of you may know, proposed that the silica for the chert came from these silica bodies in grasses. But the answer is we don't know. We don't know where it came from. Had to come from somewhere, but we don't know.
Is it the same age as the limestone? Or?
No, it would be later, but we don't know again when. I mean, it could have happened, you know, relatively shortly after the limestones were formed, or it could have happened 10 million years ago. You know, we don't. There's no way of dating it. But that's a good question. Everyone always asks it. And we have nitric paleosalt. Remember I said these really cool things that you hardly ever see. These are salt-influenced soils. So now we're in a very evaporated environment, okay? And we actually have salts. We have gypsum beds. We have halite molds. So there are some of these rocks, much like the Persian Gulf, you know, very highly evaporating environments. So we have everything from kind of wet, dry, monsoonal to semi-arid to pretty arid, evaporating. So we have that whole range of climatic conditions here. This is cool. Paleosols often have burrows of various kinds in, all kinds of insect burrows, vertebrate burrows, all kinds of things. This is actually from the just I-177, just on this side of the I-70. And these are actually lungfish burrows. They're pretty small. These were about the size of your finger. And you can see they're really dense, very closely spaced. So what apparently happened, there's probably multiple generations here, but probably what happened was that this is a fairly wet, dry climate. This is right below a vertisol, so one of these monsoonal soils. So that's the kind of environment where lungfish live. They live in temperate water bodies. So this was probably a shallow lake. Dries up. What the little lungfish do when the lake dries up, they wiggle down into the sediment. They form little called estivation chambers, and they wait it out until it rains again. And the lake fills up again. They get wet and they wriggle out and they're happy and go on. What's interesting is a very high percentage of these still have lungfish bones in them. Very, like 70% or something. It's very high. And so probably these are failed estivation burrows. In other words, you can imagine the rain didn't come the next year. So they burrowed, they estivated, and the next rainy season didn't come, and they died in their burrows. So it's kind of cool. It's kind of a cool story. And again, this is the Florence limestone. Again, one of the thickest and most chert-rich limestones. And again, this is a Schroyer, which is below it. But you can see here, notice this network. See how when you see a fresh surface, how those chert nodules actually are networked. Those are probably all replaced burrows. And burrows like these are formed generally by arthropods, shrimp-like arthropods that were burrowing in the mud. So not all. I mean, we know that some of these chert nodules formed for other reasons, but these are probably replacing burrow networks. The next interval we're going to look at is it's called the Red Hills. And this is also Permian, but it's later Permian. Okay, what we looked at before with the FLINT hills is early Permian. So that's about 280 million years or so. This is a few tens of millions of years later. So here we are, about 200. Well, this is actually early Triassic, but so late, Permian, early Triassic, paleogeography was similar. So again, what do you notice about this image that's different from the previous one?
No ice.
No ice age. Okay. One, the ice ages ended. We're now not in ice house climate anymore. Throughout the Permian, the environment has gotten drier and drier and drier as we extend into the Triassic. Triassic was one of the driest intervals globally in Earth history. So very, very warm, no ice anywhere on the planet. There were, in the Triassic, there were temperate forests above the Arctic and Antarctic circles. Very, very different world. Call it greenhouse world. So very warm and particularly in subtropics, very, very dry. And notice we don't have the big epicontinental seas pushing in anymore because of sea level oscillation has ended. And we do have, though, way down here in southwestern Texas, a tongue of the sea extending, and there's actually, as you'll see, a reef system right around this area in Texas at that time.
What part?
Big Bend?
Is that in the El Paso area, New Mexico area?
Yeah, these are what are called the Guadalupe Mountains. The Guadalupe Mountains are actually Permian in age, but they're actually an exposed ancient reef. They're a big limestone mountain range, which is actually a exhumed Permian reef system that went around the edge of this little tongue of the sea that extended.
How do you account for the Carlsbad caverns in that?
Again, those were carbonates, and also evaporites. One reason why Carlsbad Caverns was formed is it's not just limestone, it's also evaporites that were dissolved out. And that's because these basins, while there were reefs up here, the basins, very evaporitic, very dry, and accumulated hundreds and hundreds of feet of evaporites, that is gypsum and halite and other salts. So they're very, very thick salt deposits in here. And also sulfate, gypsum is a calcium sulfate. And it's actually the calcium sulfate dissolution that created a lot of the Carlsbad caverns. So yeah, they're formed in the rocks of this age. So there it is, actually. That's Guadalupe Mountains. So this is a reef limestone. This is all essentially re-exhumed Permian reef system. And again, the sediments that were forming in the basin offshore were actually hypersaline and deposited really thick layers of salts. Salts actually have banding in them. There's actually annual bands within the salts. You can do all kinds of interesting climate stuff with the salt deposits. So there they are, some of them. So these are actually varves, annual cycles. So that means there's some seasonality to the amount of evaporation or rain bringing in some fine sediments into the basin, making a little very thin layer of fine clays washed into the basin when, after a wet period. Also alternations in different types of salts. But again, these are essentially yearly bars within the salt deposits. If you look elsewhere, this is what the Lake Permian looks like. And this is the Red Hills in south central Kansas. And notice it's all red, everything's red. That's because it's really dry, very oxidized, so all the iron has been thoroughly oxidized. So these are all river deposits and floodplain deposits, basically, as well as aeolian deposits, that is wind-blown sands as well. There's also some caliche in here too, but it's mostly just red siltstones and sandstones. And that leads us then to the end of the Permian. If I was to say, what is the largest extinction event in Earth history, what would you say? Most people would say dinosaurs. Most people would say the end Cretaceous extinction. It wasn't, actually. This one was. The end Permian extinction is the largest extinction in Earth history. Estimates of as high as 90% of all the species went extinct. It was a pretty dramatic event. Completely reorganized life on Earth. And what caused it? A lot of debate for a very long time. But it's now centered, focused on this area, which is in Siberia. There's a large area in Siberia that's covered by water pouring off the front of that glacier. And that really remodeled a lot of the landscape in Kansas. So we have this is in Muncie County, areas that are mantled by these boulders. And you see these around, there's these red sandstones, well, actually they're quartzites. Originally sandstones and conglomerates, sometimes people use them for building stones, sometimes big ornamental stones that they plunk out in their yards and things. But those are actually called erratics, glacial erratics. These are carried down by the ice. So they were embedded within the ice that was moving south. So as the ice moves and entrains and picks up everything from boulders to fine sediment, powder, which becomes loess. And that's all transported in the ice, and then when the ice melts, it dumps it. So anyone know where these boulders came from? Not Wisconsin. Actually, you know exactly where it came from. Came from there. Sioux Falls, South Dakota. That's the Sioux quartzite. It's the same stuff. And this is all glacial polish. So this is all polished by the glaciers moving over it, filled with very fine sediments that kind of acts like sandpaper as it's moving over top and polishing it. Places out beautiful glacial striations. So this whole area was scoured out, and this quartzite, which is Precambrian in age, was plucked out, incorporated in the ice, carried to Kansas, and plunked down here at the edge of the melting ice. So that's where it came from. In addition to the erratics, again, we would have been here in the Flint Hills on the outwash area of the glaciers. And the two main things, or a couple things that happened was one, loess. Loess is just the fancy term for coarse silt to very fine sand that kind of grain size, it's wind blown. So what happens is that as the ice melts, it also has lots of this fine material. You get wind when it picks up, once it dries out, picks that up, carries it away from the front of the glacier and deposits it in these big, thick deposits of very homogeneous looking stuff, all very uniform in grain size. And there are actually several pulses of this because every time there was a glacial episode, you get another pulse of this stuff. And so you can't see it very well in here, but there are actually buried paleosols within this. A lot of work has been, these can be dated because they often have carbon in them, so that they can be dated. But it's in these kinds of things where they can find Native American sites and hearths and hunting sites and things like that, going all the way back to the earliest occupation of this area by Native Americans. Same thing here. This is from Missouri. This is all loess. But these little lines here are actually paleosols. So each one of these represents a land surface, a vegetated land surface for a while, and then it got buried by another big wad of loess and another soil, another land surface. It's on these surfaces if you're an archaeologist or looking for artifacts those surfaces that you focus on. So those are the ancient land surfaces. So what happens is low areas got filled in. So lots of buried valleys. So kind of completely rerouted topography. So this is actually from Milford, Lake Spillway after 93. And what's cool about this is actually re-exposed valley, side of a valley. So this was all completely covered over before the flood. And what you see right here is a person for scale. Right there, that's the edge of the valley. That's a Pleistocene valley. That's all loess filling it in. There's gravel here at the base, and then loess filling it in. So this is an ancient valley. It has no topographic expression today at all. Completely filled in by glacial Pleistocene stuff. And it was only re-exposed with this flood, washed out this loose stuff, and then you can see this edge of this original Pleistocene valley. It's kind of cool.
Is that still there today?
Yep, that's still there. It's probably all grown over and stuff, but it's still there. And there are also glacial lake deposits of various kinds. Again, water would pool and fill up. There's also places where the glacial lakes would build up and flood upstream, so the lower parts of rivers were flooded. And so when the river water came in, it built like deltas out, and so there's these kind of Pleistocene lake deltas. So all kinds of sedimentary deposits from that.
What kind of minerals would you call that purple type?
And actually that color is probably a little off. But again, it's basically just oxidized iron again.
Iron.
They can have sometimes a purple sheen to them, sometimes. And so that's Kansas 10,000 years ago. So I think that's it. Yep. Yeah, there were lions here. Yep. Yeah, there were lions. I think that there were. I think there were cheetahs too. So any questions? Any other questions? Is that helpful?
Yeah.